All right, in video 2, we're going to go through an example that really develops some important ideas. So we're given this problem of a double integral, and the domain D is off to the right, and we can tackle this. We know this is a type 3 region, so we could tackle this using iterated integrals, but it's not going to be fun. Okay, you have to, yeah, no, we're just not going to do it. So instead, we want to make our lives easier, and we remember that we really like computing iterated integrals over rectangles that are really nice, like AB cross CD, and so can we do that? So is there a mapping that we could maybe do on a nice rectangle like I have down here? And for convenience purposes, let's just call this let's call these boundaries 1. We can always scale it if we need to, okay? Let's call those 1 and 1, okay? And we're going to call that domain D star, but can we do some can we do a mapping from there to D? And really, I would like it to be invertible if at all possible, okay? So can we do this? And well, the answer is probably yes, okay? And so what I'm going to do is, what I'm going to do is I'm going to define a new coordinate system. I'm going to say that the vector from the origin out to 1, 0 is my vector u, okay, and then the vector from 0 to 1, or sorry, 0, 0 to 0, 1 is a vector v, okay? And then the other coordinate system for D that we're working in, you notice how that is labeled as X and Y. Okay, so we just need to be able to move between coordinate systems. And well, okay, this is starting to sound vaguely familiar back in Calc 2 when we had that change of coordinate systems. And we saw that those employed linear transformations. Okay? And so that's kind of the idea that we're going to do, okay? So specifically what we're going to say is to be able to get out xy. Okay, so again, I'm mapping into that xy region. I can say, well, I can certainly take some combination of u and v. I don't know what that is. I need to write that out. So to get x, okay, so I'm going to define x here as maybe this vector. Okay, and I'm going to define y as this vector, okay, and so maybe I'll just do that instead, okay. What I'm going to do here is say that x is the linear combination that is 1u plus v, okay, so notice in that coordinate system I would go over 1 and up 1, or I would use using traditional coordinate systems, this would be at the point 1, 1. So then to get this same image, I would do that. Oops, and I forgot that. And then similarly for y, I would say that this is now a minus u plus v. Okay, so then if I translate that into matrix notation, this is just going to be 1, 1, minus 1, 1. Okay. And then something that will probably come in useful later on is taking this coordinate, or this either the system of equations or the matrix that you have, and solve for u and v respectively. Now I did that on scratch paper, and so I got that u is x minus y, and I can do a vector. I don't really need it, but whatever, we'll do it, over 2. Okay, and then v was x plus y over 2. And again, that just comes from solving that system of equations in purple for the respective variables. Okay, so that's going to be really nice for us. And what this is going to allow me to do is say that when we're working in U, notice that the domain here is on 0, 1 cross 0, 1. Okay, so that's going to be a much nicer domain to work with. Okay, so then in terms of this double integral, our life becomes a lot easier. I can say that this is going to be the integral, okay, a double integral, okay, I'll worry about the bounds in a moment, okay, and let's see, if I do the substitution in here for x minus y, let's see what I get. All right, so x minus y is going to be precisely, and I misspoke, I meant y minus x, is going to be precisely, well, it'll be negative 2v, but we're going to square it, so it really doesn't matter. So I'm going to call this 2v squared, and then this becomes 2u squared. Okay, so we changed the inner part, but notice that we still have to worry about the bounds, right? I still have to worry about those, but then I also have to worry about this dx dy, okay? And so the dx dy, well, and actually I've already solved the bounds, right? Bounds are going to be 0 to 1 on each. Okay, so that's going to be nice. The dy dx is kind of the most confusing process. And so the idea with dx dy, how that's going to change, it's going to change according to area, and it's going to be kind of a scaling factor that we have to incorporate to make sure that we have equal areas here. Okay, so if I look at the area in the in D star, okay, so let's just kind of look at that. I'm going to say that the area, maybe I'll do it in green to match, the area here, if I just multiply using basic geometry, is just 1, and the area over here, okay, might have to do a little bit of geometry. This ends up being square root of 2. Oops. Not that. Okay. This ends up being square root of 2, and it's a square, so square root of 2, so the area is 2. So notice that when we convert between, or when we use the linear transformation, we're actually doubling the area from D star to D. So that means this linear transformation is actually a scaling, right? So we need to, in order to make sure that we are not changing the figure, we're not changing area when we do this transformation, we need to say that when we convert from dx dy, okay, that is going to be 2 of du dv. So we need to multiply du dv by 2 in order to get to the dx dy area. Okay, so why precisely we get this 2, we will mention in the next video, but for right now, all you can think of that when we change from dx dy to du dv, it's just a scaling. Okay, so that is going to be a new or a different way to look at this same integral using a change of variables. So instead of working with x and y, we're working with u and v, and then remember that we changed domains, right? We want to go from kind of a nasty domain to something that's a little bit more convenient, and with some transformations that make sense. And then make sure to set up bounds in our integral, substitute as needed, and then remember that this last part, the differentials, end up scaling as needed. All right, so we'll formalize this in the next video with the change of variables theorem.